Welcome back to the deep dive. Today, we are opening up a file that honestly feels a bit like a detective story. But instead of a crime scene, we're looking at the scene of a cognitive failure.
Mm.
We're tackling what might be the central mystery and perhaps the biggest frustration of modern artificial intelligence.
It is absolutely the thing that keeps AI researchers up at night. It's one of those puzzles that once you see it, you really just cannot unsee it. It totally changes how you look at every interaction you have with a chatbot.
Yeah, exactly. So we are digging into a paper today titled Measuring and Narrowing the Compositionality Gap in Language Models. And our mission for this deep dive is to focus specifically on the methodology these researchers developed. We want to understand how they measured this failure and, more importantly, the specific technique they designed to fix it.
Right, and the authors here are Offer Press and his colleagues from the University of Washington, Meta AI, and the Allen Institute. And what they've done is basically pop the hood on models like GPT-3 to show us that while the engine is massive, I mean, truly enormous, the transmission might just be missing a few gears.
That is a very apt analogy because I think, we're used to thinking of these models as basically omniscient. But this paper exposes a very specific, very stubborn blind spot. And to set the stage, we have to start with a pop culture reference, which I know is your absolute favorite way to start discussing computer science.
Well, I am bracing myself. Let's have it.
Justin Bieber.
Of course. The cornerstone of computational linguistics.
Hey, bear with me because this is the specific example right out of the paper, and I think it perfectly illustrates the madness we are dealing with here. So picture this. You have a massive, cutting-edge AI model. It has read the entire internet. It's read Wikipedia, Reddit, golf, almanacs, fan forums, just everything.
Right. It has ingested terabytes of data.
So if I sit down at my computer and I ask this superintelligence, hey, when was Justin Bieber born? What happens?
It answers instantly. March 1st, 1994. It has seen that date associated with that name millions of times during its training. It is effectively a lookup operation. It's just grabbing a fact from its memory shells.
Okay, so it has fact A. Now I ask it a totally different question. Who won the Masters Golf Tournament in 1994?
Again, instant recall. It accesses the sports data, or rather, the statistical probability of words associated with Masters 1994, and it tells you it was the Spaniard Jose Maria Olazabal.
Okay, so we've established two fundamental things here for the model. The model knows fact A, which is Bieber's birthday, and it knows fact B, the golf winner. It has these distinct pieces of knowledge in its brain.
Correct. They are sitting right there in the weights of the neural network.
So naturally, logically, if I ask it who won the Masters the year Justin Bieber was born, logic just dictates it should be able to answer that right. It's just A plus B.
And that is exactly where our human intuition about intelligence betrays us. Because if you ask that question to a standard large language model, it just chokes.
It doesn't just say, I don't know.
Well,
right?
that would be preferable. That would show some self-awareness. Instead, it often confidently answers with the wrong name. It might say Fred Couples or Nick Faldo. It just hallucinates.
That is so bizarre to me. I mean, it knows the year. It knows the winner of that year. But it just can't bridge the gap.
It cannot bridge the gap. It treats those two facts as completely disconnected islands of information. And this specific failure mode is what these researchers are calling the compositionality gap. It is the inability to compose or stitch together known facts to solve a novel problem. The model has the ingredients, it knows the recipe, but it somehow cannot bake the cake.
So the mission for today is to understand why that happens. But more importantly, we're going to look really closely at the methodology these researchers developed to fix it.
And the fascinating thing about their solution is that it isn't about building a bigger brain. It isn't about more chips or more data. It is about the logical architecture of reasoning. We're going to break down a technique they developed called SelfAsk, which basically forces the computer to stop, take a breath, and talk to itself before it answers you.
I love that. It's like mindfulness for robots. But before we get to the solution, we have to really understand the scope of the problem, because the paper drops a pretty massive bombshell regarding the size of these models.
It does, and this is where we have to talk about the scale illusion.
Okay, let's unpack this, because the general narrative in AI for the last 5 or 6 years has definitely been bigger is better.
Oh, absolutely. The scale is all you need dogma.
Right, if the model isn't smart enough, just add more parameters, throw more data at it, spend another $100 billion on GPUs, and it will get smarter. That's the industry standard approach right now.
That has been the prevailing wisdom. We've seen models grow from a few 100 million parameters to hundreds of billions. And usually when you look at the charts for translation, for coding, for creative writing, the performance line just goes up and to the right. The bigger the model, the better the result.
But these researchers decided to test that assumption specifically against this compositionality gap. So they tested a whole family of models, ranging from what they consider small, which is around 1.3 billion parameters, all the way up to the Leviathan, the 175 billion parameter GPT-3.
That is a massive difference. That's more than a 100x increase in size, complexity, and cost.
And what did they find when they tested that?
They found something that should really worry anyone banking solely on scale. As the models got bigger, they did get better at answering the single hop questions. They memorized more trivia, they knew more birth dates, and more golf winners.
So the memory improved. The encyclopedia basically got thicker.
Drastically thicker. But, and this is the really key finding here, the gap between knowing the parts and solving the whole did not shrink.
Wait, so the ratio of failure remained exactly the same?
Roughly constant, yeah. It stayed around 40%. Whether the model was a toddler or a giant, if it knew the two necessary facts, it still failed to combine them about 40% of the time.
That is wild. It implies that simply making the model bigger just gives you a really good encyclopedia, but not necessarily a better detective.
Exactly.
Yeah.
Scaling improves memorization, not reasoning. If you just make the neural network larger, you aren't teaching it how to think, you're just giving it more stuff to remember. The compositionality gap seems to be completely immune to scale.
So we're stuck with this 40% failure rate on complex questions no matter how much money we spend on training. That seems like a pretty hard ceiling for the industry.
It is a ceiling, unless we change how we ask the questions. But before we get to the how, there was one other nuance in the problem definition that I found really interesting. They looked at a metric called perplexity.
Perplexity. Okay, I've heard this term thrown around in machine learning circles. To me, it just sounds like fancy talk for how confused the model is. Is that accurate?
In a simplified way, yes. But let's dive into it a bit, because it's crucial for understanding why the model fails. Technically, perplexity measures how surprised a model is by a sequence of words. If the model is very confident that the next word is cat, and the next word is indeed cat, perplexity is low. If the next word is refrigerator, perplexity is high.
So low perplexity means high confidence.
Correct. The researchers found a very strong correlation here. They looked at how confident the model was about the underlying facts, like Bieber's birthday.
Okay.
They found that the model is much more likely to answer the compositional question correctly if it is extremely confident, meaning super low perplexity about the constituent facts.
Makes intuitive sense to me. If I asked you what is the capital of the country where sushi comes from?
I would get that right immediately. I am 100% confident sushi comes from Japan, and I am 100% confident the capital of Japan is Tokyo.
But if I asked you what is the capital of the country where the dish haggis comes from?
Okay, well, I know haggis is Scottish, but am I 100% sure Scotland is a country in this context, or is it the UK? And is the capital Edinburgh or Glasgow? I'm mostly sure it's Edinburgh, but there is a little bit of noise there.
Exactly. And that little bit of noise, that slightly higher perplexity, might cause you to stumble on the complex question.
Precisely. The researchers found that unless the model has rock-solid, near-zero perplexity on the facts, the ability to compose them just falls off a cliff. It needs a flawless foundation to build that second story of reasoning.
So we have established the problem. Models are great at memorizing, bad at connecting. Making them bigger doesn't help the connection process at all. And if they are even slightly unsure of the facts, the whole house of cards collapses.
That is the grim reality of the compositionality gap.
Enter the solution. The paper proposes a massive methodology shift. They move away from what they call direct prompting to elicitive prompting.
This is the core of the methodology, and to really understand it, we have to look at how we normally talk to computers.
We basically just bark orders at them.
Pretty much. That is direct prompting. You ask a question and you expect an immediate answer. Who won the Masters the year Bieber was born? Boom. Answer.
It's like a game show. You buzz in and you have to have the answer instantly.
Right. And consider the computational pressure that puts on the model. It has to do all the processing in one forward pass.
Explain forward pass for those of us listening who aren't deep learning engineers.
Think of it like a stream of water. The input goes in, flows through the layers of the neural network, and the output comes out. In direct prompting, the model has to retrieve the birth year, retrieve the winner, compare the dates, and formulate the name all in that one single flow of water.
Trying to sprint through a maze in one go without stopping to look at a map.
And critically direct prompting gives the same amount of thinking time to an easy question as it does to a hard one.
Oh, that's a great point. If I ask what is 2 plus 2, the model spends X amount of compute. If I ask a really complex logic puzzle, it also spends roughly X amount of compute.
Exactly. It doesn't pause to deliberate. This is where elicitive prompting comes in. The intuition here, the high-level goal, is to buy the model time, to let it talk things through before committing to a final answer.
This sounds a lot like the chain of thought method we've heard about before. You know, where you tell the model, let's think step by step.
It is deeply related. Chain of thought was the predecessor. It encourages a stream of consciousness. First, I need to find the year, then I need to find the winner, and so on.
But the authors of this paper argue that chain of thought is a bit messy.
It can be. It's unstructured. The model might ramble. It might go off on a tangent about golf course architecture. It might bury the actual answer in a massive paragraph of text. So these researchers proposed a more rigid, structured evolution of chain of thought. They call it SelfAsk.
SelfAsk, I love the name because it literally describes exactly what it does. The model asks itself questions.
It's an internal dialogue, but a highly formal one. It turns the model from a rambler into an organized project manager.
So let's get into the absolute nitty-gritty of the methodology. I want to really visualize this for everyone listening. Let's role play it. I'll be the user and you be the AI model using the SelfAsk methodology.
I am ready. I will do my absolute best to think like a machine.
Okay, step one is the prompt structure. The paper says they use few-shot prompting. That means I don't just ask the question, I show you a few examples of how I want you to behave first.
Right. You are priming me. You are showing me, look, here's a question, here's how you break it down. But there's a specific trigger phrase.
Yes, the magic spell. At the end of my query, I explicitly append the text, our follow-up questions needed here, with a colon at the end.
That phrase is the key. It forces me, the model, to stop and make a binary decision before I even try to answer. I can't just guess. I have to evaluate the complexity of the prompt.
So if I ask, what color is the sky?
I evaluate that. Is it compositional? No. Do I need sub-questions? No. So I would output no. The final answer is blue.
But now I ask you the hard one. Who lived longer? Theodore Hacker or Harry Vaughan Watkins? And I add our follow-up questions needed here.
Okay, I analyze that prompt. I see two names. I see a comparison, live longer. I realize I don't know the answer directly, so my first output, the very first thing I say is yes.
Yes, that is step two, the decision or the decomposition. You have acknowledged you need help. What happens next?
Once I say yes, the training examples guide me to generate the first specific sub-question. I need to solve the big puzzle. I need to decompose the problem. So I output follow-up, how old was Theodore Hacker when he died?
Okay, so you've identified that you can't compare ages until you know the ages. Very smart.
Right. Now here is step three, the intermediate answer. I answer my own question based on my internal knowledge. I output intermediate answer. Theodore Hacker was 65 years old when he died.
You were literally talking to yourself on a scratch pad. How old was he? He was 65.
I am. And then step four is the loop. I realize I still don't have enough info to answer the main question. I have Theodore's age, but not Harry's. So I automatically generate the next follow-up. Follow-up, how old was Harry Vaughan Watkins when he died?
And then you answer that one too.
Intermediate answer, Harry Vaughan Watkins was 69 years old.
Now you have two numbers on your scratch pad, 65 and 69.
And finally, step five, termination and synthesis. I look at my notes, I compare 65 and 69. 69 is larger. So the prompt structure requires me to output, so the final answer is Harry Vaughan Watkins.
It's so logical. It feels exactly like how I would solve a math problem on paper. I'd write down variable A equals 5, variable B equals 10, therefore A plus B equals 15.
It is explicitly mimicking that logical flow. And this structure, the follow-up to intermediate answer to, so the final answer is access scaffolding.
So why does the scaffolding matter so much? Why is this highly structured approach better than just letting the model ramble in a standard chain of thought? I mean, rambling works for some people.
There are two main reasons the authors highlight. The first is disentanglement. It completely separates the planning from the execution.
Breaking those two cognitive tasks apart.
Exactly. When you have to formulate the question first, like how old was Theodore, you are planning your retrieval. You are focusing purely on identifying what information is missing. Then when you answer it, you are executing. By separating them, you reduce the overall cognitive load. You aren't trying to find the fact and use the fact at the exact same millisecond.
That makes a lot of sense. It stops the model from getting ahead of itself and making a mistake.
But there is a second very practical reason, and that is parsability.
Parsability, that's a software engineering term, right? It means how easy it is for computer code to read and extract the output.
Yes. In standard chain of thought, the model might say, well, Theodore was 65 and Harry was 69, so Harry is older. Or it might say Harry lived longer because he was 69. Or the older one was Harry. The final answer is just buried somewhere in a messy sentence.
It's totally inconsistent. If you're writing a program to extract the answer to show to a user, that's a complete nightmare.
It is a nightmare. But with SelfAsk, the prompt requires the model to say, so the final answer is followed by the short result. It is strictly formatted every single time.
The paper actually had a stat on this, didn't they? Comparing the parsability.
They did. On one of their datasets, the Bamboogle dataset, which we will definitely discuss later, chain of thought, failed to give a clean, short-form answer 40% of the time.
40%. That's almost half the time the answer was unusable programmatically, even if the logic was right.
Exactly. Even if the reasoning was totally sound, the output was messy, whereas SelfAsk only failed the formatting 17% of the time. So simply by enforcing this rigid Q&A structure, you make the model significantly more reliable and easier to integrate into actual software.
Okay, so we have a methodology where a model talks to itself, breaks down problems, and gives clean parsable answers. That alone sounds like a massive win for the industry. But there's a twist in this paper, and this is the part that I think is really cool.
The search engine integration.
Yes, because here is the lingering problem. Even if the model asks itself perfectly, when was the Eiffel Tower built? It's still relying on its own internal, potentially flawed memory to answer it.
Right. And as we discussed with the perplexity issue earlier, if the model has hallucinations or false memories, the whole reasoning chain just collapses. Garbage in, garbage out. If it confidently thinks the Eiffel Tower was built in 1800, the final math will be wrong no matter how good the logic is.
So the researchers realized that the specific SelfAsk structure gave them a perfect opening to intervene in the process.
A man in the middle attack but for accuracy.
A benevolent man in the middle.
Exactly, because SelfAsk explicitly outputs the text follow-up, and then a question the researchers realized they didn't have to let the model answer that follow-up itself. They wrote a very simple piece of code to just watch for that tag.
Okay, walk us through the flow here. The model says, follow up, who is the president of France?
The code sees that text and immediately hits the pause button on the model. It completely stops the text generation. It takes that text, who is the president of France, and sends it to a Google search API.
So it literally Googles the sub-question that the AI generated.
It Googles it. The search engine comes back with the answer Emmanuel Macron. The code then takes that external fact and inserts it back into the model's text stream as the intermediate answer.
So the model thinks it answered the question itself.
Or it just sees the answer appear on its scratchpad. It doesn't really care where it came from. It just resumes generation from that point. Intermediate answer, Emmanuel Macron. Then it moves seamlessly to the next step.
That is absolutely brilliant. You are essentially offloading the memorization requirement to the internet and keeping the reasoning requirement inside the AI.
Precisely. You turn the language model into a reasoning engine and a query generator rather than a static knowledge base. And this solves the update problem instantly.
The update problem. Tell us about that.
If the president of France changes tomorrow, a standard GPT-3 model won't know that until it is retrained, which takes months and millions of dollars. But a SelfAsk model connected to Google, it knows instantly.
Because it's not relying on its frozen weights, it's fetching live data every single time.
Exactly. And the best part about this specific approach, the paper emphasizes this in bold letters. No fine-tuning.
None at all.
Zero. They didn't retrain the model. They didn't update a single weight in the neural network. This is purely a prompting technique. You could do this with GPT-3 right now without access to the source code, provided you can just script the API calls.
That democratizes the capability significantly. You don't need a supercomputer to retrain the model. You just need a clever Python script to watch the output.
It creates a totally modular system. It suggests that the future of AI isn't one giant, monolithic brain that knows every single fact in the universe. It's a brain that knows how to find everything.
This really feels like the future of these assistants. They shouldn't just be know-it-alls. They should be active researchers.
It is certainly a much more robust architecture, but to prove it actually worked, they had to rigorously test it. And standard tests just weren't good enough for this.
Right, because if you test on standard questions, the model might have just memorized the answers during training. If you ask what is the capital of France, that's not testing reasoning. That's testing rote memorization. They needed questions that definitely weren't on the internet.
So they built two brand new data sets. The first one is called Compositional Celebrities, or CC.
Which honestly sounds like a reality TV show I would absolutely watch.
Who can compose the best poem while stranded on an island? No, it was an automated data set. They took lists of celebrities, their birthplaces and birth years, and then mashed them up with other completely random facts in highly unlikely ways.
Give me an example of an unlikely way from the paper.
What is the calling code of the birthplace of Mila Jovovich?
Okay, yeah. That sentence has almost certainly never been written down in human history.
Exactly. The model knows Mila Jovovich. It knows her birthplace is Kiev. It knows the calling code of Ukraine is +380, but it has never seen the sentence. The calling code of Mila Jovovich's birthplace is +380. It has to compose it right then and there.
So that tests the pure reasoning mechanism. It forces the model to go, step 1, find birthplace, step 2, find calling code of that place.
Correct. But then they made the real boss-level data set, Bamboogle.
Bamboogle, a fantastic name. Sounds like a really aggressive dance move.
It's a manually crafted data set of only 125 questions, but they were specifically designed to be Google-proof.
Google-proof. That's a pretty bold claim considering Google basically knows everything.
The criteria for inclusion was strict. If you type the whole question into Google, the featured snippet, that bold answer right at the top of the page had to be wrong or misleading.
Oh, I hate when that happens in real life. When Google tries to be too smart and gives you the wrong summary because it grabbed the wrong keyword from some article.
Right. So the researchers specifically looked for those traps to put into Bamboogle. A really great example from the text is who was the head of NASA during Apollo 11.
Okay, I feel like I should know this one.
Most people, and Google's algorithm might jump straight to Gene Kranz. He was the flight director. He's the guy in the white vest in all the movies.
Failure is not an option. Ed Harris.
Exactly. So Google often highlights him because his name is so strongly associated with Apollo 11 and leadership in the text data. But the actual administrator of NASA, the actual head of the agency, was Thomas O. Paine.
So to get that right, you can't just do a simple keyword search and grab the most popular name. You really have to understand the organizational hierarchy of NASA, the specific date of Apollo 11, and cross-reference them accurately.
It requires genuine multi-step reasoning. That is why Bamboogle is such a brutally tough test. It forces the model to ignore the obvious statistical association and dig deeper. It tests whether the model can resist the urge to just hallucinate the most popular answer.
So we have the method SelfAsk, we have the upgrade, which is the search engine, and we have the exam Bamboogle. How did they do? What were the actual results?
The results were stark. First off, the baseline. Direct prompting, just asking the question, performed very poorly on these complex tasks, exactly as we expected from the compositionality gap discussion earlier.
No surprise there. The gap held strong.
Then they compared SelfAsk against chain of thought. And remember, chain of thought was the reigning champion of reasoning methods at the time. On the Bamboogle dataset, SelfAsk beat chain of thought by a huge margin, an 11% absolute improvement.
11% is huge in AI benchmarks. Usually researchers fight for like 1 or 2% to get published.
It is massive, and the authors argue this is largely because of the structure. Bamboogle questions are highly unique and varied. Chain of thought struggled to organize its thoughts for these very novel problems. SelfAsk's rigid ask a question, answer it loop handled the novelty much, much better. It serves as a reliable algorithm for thinking.
It effectively standardized the internal thinking process regardless of the question type.
Exactly. And what about when they plugged in the search engine?
The moment of truth.
The numbers went up even further. On some metrics, adding the search engine improved accuracy by another 10% or more. It really turns a B student into an A student.
That makes total sense. It's like letting a student use an open textbook during a really hard exam versus forcing them to do it purely from memory.
Exactly. But there was one more comparison that I found really important for the people actually building these applications in the real world. Efficiency.
Yeah, computing power costs serious money. Every token generated costs a fraction of a cent, but when you have millions of users, it really adds up.
There is another method called least to most prompting, which also attempts to break down problems. But it requires running the model multiple times, multiple separate passes. You ask the model to decompose the question, then you have to take those sub-questions and feed them back in one by one. It's slow and it's expensive.
And SelfAsk. How does it compare?
SelfAsk runs in a single forward pass. The model just keeps talking. It generates the question, the answer, the next question, the next answer, all in one continuous go. It is significantly faster, uses fewer tokens, which translates directly to lower cost, and achieves similar or even better accuracy.
So it's smarter, it's more accurate, and it's cheaper. That is basically the holy grail of software development.
It effectively is. It shows that you don't always need a highly complicated multi-stage architecture. You often just need a really good, well-structured prompt.
This whole deep dive has really changed how I look at these large language models. I think we tend to treat them like magic 8 balls.
Yeah.
You just shake it and hope for the right answer to pop up.
And this paper strongly suggests we should treat them much more like junior analysts. You don't just shout a complex question at a junior analyst and demand an answer in 1 second. You give them a clear process. Go look this up, then look that up, then synthesize it and come back to me with the conclusion.
And when you give them that process, that self-ask structure, they suddenly become so much more capable.
It completely bridges the gap. It dramatically narrows that compositionality gap that we started with. It essentially proves that the limitation wasn't necessarily in the model's brain capacity, but in how we were asking it to use that brain.
So let's wrap this up with a nice summary of what we've learned today. We've covered a lot of ground, and it's a pretty dense methodology.
Sure. Let's recap the methodology specifically because that's really the core takeaway here for anyone listening. First, we identified the underlying problem, the compositionality gap. Models are great at memorizing isolated facts, but terrible at combining them to solve new multi-step problems.
And surprisingly, making the model 100 times bigger doesn't fix this at all, the scale illusion.
Right. Second, the solution is elicitive prompting, specifically the SelfAsk method. By forcing the model to explicitly output the phrase, "Are follow-up questions needed here?" and then generating a highly structured Q&A with itself, we create a very robust scaffold for reasoning.
We force it to logically plan before it wildly executes.
Third, this rigid parsable structure allows us to easily plug in external tools like Google Search, the man-in-the-middle approach. This fixes the hallucination problem and keeps the model up to date with current events without any expensive retraining.
And finally, this method soundly beats the previous best-in-class approaches like chain of thought, especially on tricky, novel questions like those found in the Bamboogle dataset.
It is a resounding triumph of methodology over brute force compute.
Which leads me to my final thought for you, the listener. In this industry, we are so obsessed with parameter counts, right? GPT-4 is bigger than GPT-3. This new model has 1 trillion parameters. But this paper showed that the cognitive gap didn't shrink, even when models grew from 1 billion to 175 billion parameters.
Right. The hardware scaled massively, but the actual reasoning didn't scale at all.
So if size alone doesn't solve reasoning, but a simple change in how we structure our talk to the model does, are we focusing on the completely wrong things? Are we spending billions of dollars building bigger brains when we should really be spending more time teaching the brains we already have how to think?
That is the multi-billion-dollar question for the whole field. It heavily suggests that prompt engineering, or rather cognitive architecture, might be just as important, if not more so, than raw compute. It suggests that true artificial intelligence isn't just about capacity, it's about process.
Definitely something to think about the next time you type a prompt into a chatbot. Maybe try asking it to ask itself some questions first.
It certainly couldn't hurt. In fact, based on the methodology in this paper, it might just be the smartest thing you can do.
Thanks for joining us on this deep dive into the architecture of reasoning. We'll catch you on the next one.
Goodbye, everyone.